Yeah, good afternoon. Welcome to Compass Wednesday. Our speaker today is Professor Henry Potter of the Texas A&M University. And Henry is a former AMP graduate student here at Erasmus. He was one of the first AMP students I met after I had arrived here in 2008. He started in 2009, but let's go through his CV from the beginning. He grew up in England and then he came to the US. He went to the Southern Maine Community College in Portland, Maine from 2003 to 2006. And then he went to Indiana University, got a bachelor's degree in geography in 2009. And then he came to Erasmus to study AMP, and he got a PhD in AMP, Applied Marine Physics, in 2014, working with Will Drennan and Hans Graeber, I think, mostly, right?
Right.
And then he went to the Naval Research Laboratory in Washington, D.C. for 2 years, 2014 to 2016. And in 2016, he started at Texas A&M University as a visiting assistant professor in the Department of Oceanography. And in 2017, he became assistant professor. The bell is ringing here. Let me switch that off. And yeah, so he's now an assistant professor there in Texas A&M, still working on RC interactions, as you will see. He has 17 peer-reviewed publications, if I have counted that correctly. I think 10 of them as a first author. He has given many presentations and a few invited presentations. He has a bunch of grants here as a PI and as a co-PI. He has been in several field experiments, the latest ones here since 2017 as chief scientist. He has been an invited panelist at an AGU meeting. He has convened an AMS meeting on RC interaction. He is a member of a subcommittee on ocean-atmosphere interaction. He has been vice chair, or he was the vice chair of the AMS committee on RC interaction. So he is becoming a more important guy in the community. And he contacted me and Brian Soden a few months ago to suggest to us that we should do more for our former students, maybe start to organize a seminar series for former students, which is good for them because they are in a position like Henry. It's good to have invited presentations at other places. That's good for their CV and for their career. And of course, for our current students, it's good to get examples of what our former students are doing now. And we may be developing something like that. For now, we just invited him to speak in the regular Compass seminar, and he agreed to do it, which is very nice. And his title today is Upper Ocean Temperature Variability in the Gulf of Mexico with Implications for Hurricane Intensity. So welcome to Compass, Henry. Nice to see you again.
Thank you very much.
And please go ahead. And
yeah, go ahead and share my screen.
Yes.
I actually thank you very much for the very thorough introduction. I'd actually forgotten that you are the guy who reads the CV word for word. So if I'd remember that, I would send you an abridged version. Nonetheless, it's very nice to be here. Thank you very much for the invitation. So this presentation I'm going to give to you today is, well, it's upper ocean temperature variability in the Gulf of Mexico with implications for hurricane intensity. This is some work that I recently had published, and I actually worked with Jonah Rudsin, who is also a Erasmus graduate. She worked under Nick Shea, and let's see, she went to Monterey for a couple of years to work at the Naval Research Lab there, and now she's, I believe, at Mississippi State as an assistant professor. Okay, so let's just start off with a little bit of background on why we like to study hurricanes. So here's some data. There's been 1,830 storms, Atlantic hurricanes since 1851, of which 567 were in the Gulf of Mexico. Gulf of Mexico is going to be the focus of my talk today. That means there are about 7 hurricanes each year, or about 2 a year that strike the US. 3 major hurricanes, which are category 3 or greater, strike the US every 5 years. 40% of all US hurricanes hit Florida. 88% of all major hurricanes hit Florida and or Texas. Of course, some hurricanes hit Florida and then they hit Texas. And 65 hurricanes have hit Texas since 1851. And the 6 most costly consumer price index adjusted US weather and climate disasters are all hurricanes. That is Katrina, Harvey, Maria, Sandy, Irma, and Matthew. So here's some pictures from Hurricane Harvey just to drive home how destructive they can be. I'm sure I could produce another slide just like this related to any hurricane that hit Florida or any other Gulf states. So Hurricane Harvey caused 90 deaths and $130 billion in damages. It was 7th most deadly and 2nd most costly when it hit Texas coast in August 2017. And it dumped 60 inches of rain on Houston. So these images here are just of Houston and the area. This is the one in the middle here. This is Harvey just before it made landfall in Rockport. And then on the left here, we can see some flooding in Houston on one of the interstates, 610 maybe. Up in the top right corner here, we can see some flooding in some, subdivision or some neighborhood. And this picture in the bottom here, this is kind of a weird one on the bottom left. This is the Texas World Motor Speedway, which is just down the road from here. And as far as I'm aware, they've never used it for, well, as long as I've been here, they've never used it for any racing. But what they did with it after Hurricane Harvey was they used it as the storage spot for all or a lot of the cars that were damaged during Harvey. So what you can see in this image here is just a bunch of destroyed cars just sitting at the Texas Motor Speedway just down the road from here. So hurricane forecasts intensity, which is what I'm going to talk about, is obviously important to get it right. In fact, the National Hurricane Center are doing a great job at improving hurricane forecasts. The forecast error is still in the range of about 10 to 20 knots at the annual average. You can see here a nice schematic that I took from National Hurricane Center a couple of days ago. National Hurricane Center official intensity error trends in the Atlantic Basin. This is just delineated by the forecast, whether it's 120-hour forecast, 96-hour forecast, etc. So we can see that the forecast accuracy is really getting a lot better, but there's still a little bit of uncertainty here. And remember, this is the annual average, so there'll be some variability here associated with individual storms. So the motivation of this work is, I guess, in aid of helping these forecasts or giving these forecasters information that may help improve their accuracy. Tropical cyclones extract their energy from surface entropy fluxes. So by first approximation, intensity is a function of sea surface temperature. That's been known for quite a long time. And you can see here we have a sea surface temperature satellite image. And so this sort of resource is incredibly useful when trying to forecast hurricanes. However, surface forcing by tropical cyclone winds creates currents and waves which mix the upper ocean, reduce the sea surface temperature, and decrease the enthalpy fluxes, which hinders the ability to intensify. So while these sea surface temperature maps are very helpful, they don't provide a great deal of information, well, they don't provide any information about below the surface. So here's an image of the impact that a hurricane will have on the upper ocean. So here we just have a couple of a couple of images of storms that are moving down the page, so they're moving towards us. And as they move towards us, they create these currents and they create these waves, and it causes a lot of mixing, which brings cold water to the surface. And on the image on the left here is the response that you would get when you have the cold water below the surface. When cold water is just below the surface, that is to say when the thermocline is narrow, when the mixed layer is narrow. When the mixed layer is deeper, you get a much muted sea surface temperature response. But in both cases, the sea surface temperature is being cooled by the storm, which in itself reduces the entropy fluxes and impacts the ability for a storm to intensify. So that's called a cold wake. So a cold wake is a temperature decrease resulting from enhanced mixing and upwelling. It is induced by surface wind stress, which creates divergent surface currents and large waves. This is a great image that I took off. It's a NOAA image which is sea surface temperature anomaly following Hurricane Igor in 2000. And you can see quite clearly here that the hurricane crossed the Atlantic, and as it crossed the Atlantic, it reduced the sea surface temperature. This image comes from some ITOP data. So when I was doing my PhD at University of Miami, I was involved in the impact of typhoons on the ocean in the Pacific experiment. And we collected some flux data, but we also collected some subsurface temperature data. And this image is adapted from one of the papers that I published as a result of that experiment. So what we're looking at here is sea surface temperature in the upper image and the subsurface temperature in the lower image as a function of day of year. So we have, what is that, like almost a month of data. And now what you should be able to see here is that there's a couple of locations here. I don't know if you can see my cursor, presumably you can. Here and here where the sea surface temperature was decreased, and that was because there were a couple of typhoons that came through. So the first one that came through here was Typhoon Megi, and then the second one here was Typhoon Chaba. So you can see that they both decreased the sea surface temperature. Megi, not so much. Chaba, quite a lot. That was a result of the intensity of the storm and how close it was to our mooring. You can see the sea surface temperature response. You can also see the subsurface temperature response. And what's clear here is that the water is upwelled and mixed, and it's not just the surface that decreases in temperature, but the whole water column here, at least at the top 100 is decreased in temperature. And that decrease in that sea surface temperature decrease is going to impact the ability for a storm to intensify. So here's a couple of little bullet points here. Sea surface temperature decrease tends to be greatest for stronger, slow-moving tropical cyclones with shallow mixed layer depth and with a sharp thermocline gradient. Great. And when the barrier layer thickness, that is to say, the vertical distance between the mixed layer depth and the isothermal layer depth is small. When statistical tropical cyclone models account for stratification and associated feedback arising from vertical mixing and surface cooling in lieu of sea surface temperature alone, model performance is improved. So that brings us to this metric that's going to be at the heart of my presentation, which is tropical cyclone heat potential, which is the depth integrated heat above 26 degrees. This was first introduced by Whitaker in 1967 as hurricane heat potential and often referred to as ocean heat concept. This guy, by the way, I traced this tropical cyclone heat potential back. He was a master's degree student here at Texas A&M University. Anyway, then this metric was popularized by Lieber and Vogenu in 1972, who recognized that when sea surface temperature decreases between the air temperature, energy is not readily extracted from the sea and the hurricane can no longer be sustained. And they wrote, the rate at which surface temperature decrease occurs determines the change in rate at which energy is fed into the storm. In other words, tropical cyclone heat potential is a metric used to try and account for subsurface structure that influences the magnitude of sea surface cooling. So tropical cyclone heat potential, this is the equation for tropical cyclone heat potential. And it's an integration or a summation. So here we have the specific heat of water multiplied by the sum or the integration between the temperature from the surface down to the 26-degree isotherm, multiplied by the density of water at each level, multiplied by the temperature in excess of 26 degrees, the temperature of the water in excess of temperature of 6 degrees, and then the water layer thickness. So in the left image, so both of these images here show typical upper ocean temperature profiles. This is just the top 100, sorry, top 200 meters. So we have temperature on the x-axis here and depth on the y-axis. And the blue lines mark the depth of the 26-degree isotherm. So in essence, what the tropical cyclone heat potential is a measure of how much energy is in the water in excess of 26 degrees between the surface and the 26-degree isotherm. So on the left, this image has the profile on the left has a tropical cyclone heat potential of 70 kilojoules per centimeter squared. And on the right, it has 9 kilojoules per centimeter squared. These are quite different values. And the reason we have different values here is because firstly, the image on the left, the 26-degree isotherm is quite a lot deeper. It's below 50 meters. So you have more of the water column to extract energy from. And the second reason is that the temperature of the water is warmer. Here you can see the sea surface temperature is in excess of 30 degrees. This one here is maybe at 27 or something like that. So that's how we get our tropical cyclone heat potential. Now, if we go back to this image from ITOP that I just showed you, it's essentially as it was before, but now I put this red line in here. This shows us so this is the 26, so I've just marked 26 degrees here, okay? So as long as the sea surface temperature is greater than 26 degrees, then the hurricane has the ability to extract heat from the ocean, because the water theoretically is warmer than the atmosphere. Once the sea surface temperature decreases below 26 degrees, then the gradient is in the other direction, and it's a lot more difficult to extract heat, which in turn impacts the ability for a storm to maintain itself or intensify. Now, a really useful product which is produced by NOAA and OML is this tropical cyclone heat potential maps that they get using satellite information. So the way they do this, my understanding, is they can get the sea surface height anomaly, which is in this figure here. And so they can figure out the sea surface, that's from an altimeter, they can get the sea surface height anomaly. They know what the sea surface temperature is, they can also get that from satellite. And then using those two pieces of information, plus I believe it's historical hydrographic information, they're able to create these tropical cyclone heat potential maps. And these maps are incredibly useful because they provide additional information which can be used in models to try to improve the accuracy of forecasts. So a few little bullet points here. Tropical cyclone heat potential greater than 60 kilojoules per centimeter squared is required for strengthening. This is generally accepted understanding that if you have kilojoules greater than 60 kilojoules, then you can strengthen your hurricane. Very high tropical cyclone heat potential, that is like 90 or greater, which are typically associated with the loop current, and loop current eddies are associated with sudden intensification of tropical cyclones. And there's lots of people, University of Miami in particular, who have spent time thinking about this. And that's quite clear actually in this map. You can see that although there's not the water coming in from the Caribbean and as part of the loop current, although the loop current is looking pretty weird in this figure actually, is a lot warmer than the Gulf of Mexico as a whole. You can also see this loop current eddy right here, which also has much higher tropical cyclone heat potential than the surrounding water. So here the loop current eddy has whatever, 100 kilojoules per centimeter squared. Including altimeter-derived sea surface temperature results in more accurate forecasts than sea surface temperature alone. This is reference to Manelli back in 2008. So tropical cyclone heat potential is a very useful metric, and we can come up, NOAA and AML come up with this great product that can be used as part of hurricane forecasting. Now, it becomes a bit more nuanced than that. And I'm going to give you a couple examples of situations where this idea of having a certain amount of tropical cyclone heat potential is necessary to intensify storms isn't necessarily true. So the first one comes from this data that I collected back in 2007. And during that time, Hurricane Harvey intensified on the Texas shelf. So here you can just see on the image on the left here, you can just see the Hurricane Harvey's track. And then in white here, you can see these numbers here are the intensity of the storm as it approached land, and then just the time of the time of each one of those intensity changes. And then I've zoomed in a little bit here. So this is just before it made landfall. This black polygon here is the area where I was part of a hydrographic survey. So I collected data there prior to the storm, and it's worth noting that as Harvey crossed over the shelf here, it intensified, continued to intensify. Now, the hydrographic survey, what it showed was that Hurricane Harvey intensified on the shelf despite tropical cyclone heat potential being just 35.1 kilojoules per centimeter squared. So it's much lower than the value that typically associated with intensification. So these images here on the left show the location of various CTD. So each one of these is a CTD cast, and the temperature of the water column is given by the color bar here. So these were the temperature profiles, and this was done 2 weeks before Harvey made landfall. And then this blue line here marks the location where we did a acrobat tow. So an acrobat is essentially what would you call it? Like a towed underwater aeroplane. It has a CTD on it, so you can pull it along, and indeed we pulled it along this transect here, and it just recorded various parameters, but one of them was temperature as a function as it went along. So it went on there, and this is what the temperature profile looked like in this region here. So what we found was that up to 50 kilometers from shore, tropical cyclone heat potential was limited by the depth of the water, not by the 26-degree isotherm. A narrow region of sub-26-degree water meant that mean water column temperature above 28 degrees was typical, which means that a complete mixing of the water column did not substantially decrease the sea surface temperature, and therefore conditions may remain favorable for intensification. My co-author, although I didn't know it at the time, had a similar finding when she was studying hurricanes as they were passing through the Orinoco, the Orinoco outflow. So Hurricane Ivan and others rapidly intensified a region with tropical cyclone heat potential approximately 40 kilojoules per centimeter squared. So just to orientate yourself there, we have this data here is an ocean heat content map, and it's this region here in the Caribbean. And the storm intensity is given by this red bar, this track here. And what she found was that there were several hurricanes which underwent rapid intensification over regions with relatively low tropical cyclone heat potential near the Lesser Antilles. Sea surface cooling was similar to high tropical cyclone heat potential regions because vertical salinity stratification induced by the Amazon Orinoco river plume reduced entrainment of polar water across the subsurface. So here we have another situation where storms are actually able to intensify even when the heat potential is not as high as you necessarily expect for intensification. So Hurricane Harvey intensified with tropical cyclone heat potential about 37. Hurricane Ivan and others rapidly intensified with tropical cyclone heat potential around 40. And intensification is not expected at these tropical cyclone heat potentials. Recall that about 60 is needed. So that led me to the question, what other conditions lead to inequity in tropical cyclone potential? And just as a teaser here, I want to show you these two images. And so we have two temperature profiles from the surface down to 200 meters. Again, it's depth on the y-axis and temperature on the x-axis. Both of these profiles have the same tropical cyclone heat potential. They both have tropical cyclone heat potential of 59. The blue line in each image is the depth of the 26-degree isotherm. So that's the depth you would integrate to. That's the depth you would integrate to if you were looking to calculate the tropical cyclone heat potential. So in each case, you can see it's very different. And the orange line is the depth you would need to mix the water column to in order to reduce the sea surface temperature to 26 degrees. So in the case on the left here, if you wanted to reduce your sea surface temperature to 26 degrees and in essence reduce your tropical cyclone heat potential to 0, you'd need to mix the water column to 170 meters, which is no small undertaking. On this image on the right, you can reduce the sea surface temperature by mixing the water column to about 90 meters. So I think this is a good example of how inequities exist in this idea of TCHP. So this is the data source. I used Argo. I'm sure you all recognize this guy here. This is Boris Johnson. I have no idea what he's doing, holding on to an Argo float. And presumably he's trying to promote ocean literacy or something. When I showed this to my wife the other day, she said it looked like a giant needle. Maybe he's trying to encourage people to get that. Anyway, I'm sure you all know what Argo is, but just for those of you who don't, an Argo float is, well, it's a float that drifts around the ocean. And this is essentially the life cycle, if you will, of an Argo float. So they float around the ocean, they come to the surface and they relay information, then they descend to about 1,000 meters, and then they drift around for about 9 days, and then they descend to about 2,000 meters. It's not always the case, but they descend to 2,000 meters, and they rise up to the surface over the course of several hours. It's a 6-hour ascent, and as they ascend, they record temperature, salinity, and pressure or depth. Temperature salinity profile recorded during the ascent, and they're typically about meters spaced about temperature, salinity measurements, maybe spaced about 1 meter apart, maybe a little bit more than that. They come to the surface, they relay that information back to land, which is then made available in near real time. And then the cycle goes again. They sink back down, they spend 10 days underwater, and then they come back up and make another. So Argo is the data that I used for this research. These are Argo float locations throughout the world today. See, I put a little asterisk there because I knew that I would forget to update it. So you can see this was actually October the 2nd, and I think today's maybe the 6th. So this is the Argo locations throughout the world 4 days ago. But nonetheless, you can see they're all over the place. And it's a great asset for those of you that haven't used Argo in the past. They're really, really useful, great resource for ocean research. And there's about 4,000 of them in use right now. And I guess that means, let's see, they come up every 10 days. So that means you get 400 profiles a day added to the database. So I was studying the Gulf of Mexico, and so I was just using Argo profiles that were recorded in the Gulf of Mexico. So here we have Argo float profile locations in the Gulf of Mexico during hurricane season, which is June to November from 2003 to 2019. That includes the loop current and the loop current eddy. Okay, so a couple of things here. Firstly, 2003, I don't know why I have 2003. There are basically no Argo profiles in 2003 in the Gulf of Mexico. They didn't really start coming in force until 2010. Maybe there's a couple in 2003, so that's essentially incorrect. It should be 2010 to 2019. The other thing is, and this is important, I didn't use any data that was recorded in loop currents and loop current eddies because we already know a lot about loop currents and loop current eddies and how they impact hurricane intensity. So I wanted to restrict my data to profiles that were recorded outside of those, outside the loop current and the loop current. And there were 4,415 profiles that we used for this research. So let's talk a little bit about data processing. So on the left here, we have just the temperature profile. Here, I just have the top 200 meters. Again, we have temperature on the x-axis and we have depth on the y-axis. And this is the location of that particular profile. Okay, so we have, that's our first data point. And now from that data point, from that profile, I extracted several pieces of information. The first thing is the sea surface temperature, this blue line up the top here. The second one is the mixed layer depth, which is, in this case, is 8 meters. That's the red line. And then I identified the isothermal layer depth, and that was where the temperature was 0.5 degree cooler than the surface. And then I identified the depth of the 26-degree isotherm. And then I calculated the barrier layer thickness. Remember, the barrier layer thickness is the difference between the mixed layer depth and the isothermal layer depth. And finally, I calculated the tropical cyclone heat potential, which in this case was 70 kilojoules per second. So from that profile, I got those 6 pieces of information. Okay, and then I just put them in this table. So here's my first profile, and these are the variables that I just introduced, just calculated. And then I do it for my second profile, and I'm just filling in this table. And then I do it for my third profile. And I keep going until I've done it for all 4,415 profiles. Okay. So then I have this table. I have 4,415 observational units, and then every one has 6 different variables associated. Now, because I'm going to be doing a principal component analysis. One of the things I need to do before I can complete the principal component analysis is normalize the data. So that's what I've done here. So now I've just normalized the data, and then I can do my PCA, my principal component analysis. And here's the initial results of the principal component analysis. So on the left here, we have the scree plot. On the right here, we just have a scatter plot of the first 2 modes. And then on the bottom, we have a table that shows the proportion of explained variance. So what does this tell us? This tells us that the first mode, which is the first mode, explains 42% of the variance in the data. The second mode explains 33% of the variance in the data, which means collectively the first 2 modes explain 75% of the variance in the data. And the third mode explains 90% of the variance in the data, which means the cumulative variance is 94%. So the power of the principal component analysis, for those of you that aren't familiar with it, is that you can start with a lot of variables and you can reduce the dimensionality of your data set. We start off with 6 variables, right? And with just 3 new variables, these 3 new modes, we're able to explain 94% of the variance in the data. So we've reduced the dimensionality of the data set. And we've also ordered the modes in terms of how much of the variability they can explain. So these are the 3 modes that I just showed you in the previous slide. So mode 1, mode 1, I apologize. Mode 1 is given by this equation here. Mode 2 is given by this equation here, and mode 3 is given by this equation here. So for those of you that aren't aware, the these values in parentheses here are the loadings or the coefficients, and collectively for each mode they make up the eigenvector. And the eigenvectors are the values of normalized, are the values that the normalized observational data are multiplied and summed in order to give you the score, the mode 1 score, the mode 2 score, etc., which are the new variables in the principal component space. So the first mode, my interpretation of the first mode is that any observation with a high mode 1 score will have a deep, well-mixed upper ocean, a narrow barrier layer, a deep 26-degree isotherm, and a relatively high tropical cyclone heat potential. For mode 2, any observation with a high mode 2 score will have a very high sea surface temperature and tropical cyclone heat potential, a relatively shallow mixed layer and isothermal layer depth, and a relatively deep 26-degree isotherm. And for those of you that are having problems following along, the interpretation here is taken from these equations. So what would give you a very high mode 2 score would be if you had a high sea surface temperature, because the loading for the sea surface temperature is large. If you had a high tropical cyclone heat potential, it's also going to contribute to a high mode 2 score. And then for mode 3, my interpretation is that a high mode 3 score occur in cold water with a shallow mixed layer, a deep isothermal layer, and a very thick barrier layer. Okay, so we'll come back to this several times. These are characteristic profiles that represent each of the 3 different modes. So when you think of mode 1, when I talk about mode 1, think of a profile that looks like this. It has a deep, well-mixed upper ocean. It has a narrow barrier layer. It has a deep 26-degree isotherm, and it has a relatively high tropical cyclone heat potential. When you think of mode 2, think of a profile that looks more like this. This has a very high sea surface temperature and tropical cyclone heat potential, and a relatively shallow mixed and isothermal layer, and a relatively deep 26-degree isotherm. And mode 3, we're not going to talk about that, so we can just move on. For reference here, these first two, mode 1 and 2, in these cases have tropical cyclone heat potential of about the same. This one has a very small tropical cyclone heat potential. We call those characteristic profiles. So these are box plots of mode scores by month. So if I take my mode 1 scores and I plot them by month, this is what it looks like. If for mode 1, it starts off low and increases essentially linearly throughout the year, with the highest mode 1 scores existing in November, lowest existing in June, which means, doesn't matter what it means. Then these are for mode 2, mode 2 scores look like this. So mode 2 scores start off relatively low in June, they peak in August, and then they decrease again and they're lowest in November. By the way, mode 1 scores are all significantly different per month. Mode 2 scores are significantly different except for September and June. And these are mode 3 scores. I'm not going to talk about these, so we'll just move on. But this is what the mode 3 scores look like. Now, taking a look at those box plot of mode scores again, for mode 1 and mode 2, which is the focus of this presentation moving forward. And if we put those next to a time series of variables used in the PCA, I think it becomes a lot clearer to understand why we have these particular trends. So if we take a look at mode 1, which increases throughout the year, and remember, mode 1 is driven primarily by having a deep mixed layer and a deep isothermal layer and a deep 26-degree isotherm. And if we look at this figure on the right, we can see that the mixed layer, the isothermal layer, and the 26-degree isotherm all increase throughout the year. And since these are driving mode 1 scores, it stands to reason that mode 1 scores are going to increase throughout the hurricane season. Mode 2, recall that mode 2 is mostly sea surface temperature and tropical cyclone heat potential driven. And so if you take a look at your mode 2 score as a function of month, and you compare it to the sea surface temperature and the tropical cyclone heat potential, you can see a very clear pattern or similarity between these two, right? Because the mode 2 scores are driven primarily by tropical cyclone heat potential and sea surface temperature. Okay. Here's the Brunt-Väisälä frequency. I won't spend too much time on this, but the Brunt-Väisälä frequency, which is a measure of stratification, can be calculated, use this equation right here, where we have gravity and density, and then we have the change of density with depth. And I calculated the Brunt-Väisälä frequency from the isothermal layer depth to the isothermal layer depth plus 30 meters in order to quantify the stratification across the thermocline. And what I found, so on the left-hand side here, let's pay attention to the figure on the left to start with. What I found was that mode 2 water has a sharper peak incline below the isothermal layer depth than mode 1, which is demonstrated here by these two histograms, right? So mode 1 distribution of Brunt-Väisälä frequency, and then mode 2 is in orange. You can see that mode 2 has a slightly higher Brunt-Väisälä frequency, which means that it has a sharper peak incline. Now I repeated that analysis, but the second time I did it, I used a uniform salinity to help calculate the density. And in that case, I found that the pattern remains essentially the same, but they get shifted to lower values. Using a constant salinity rather than the observed salinity to calculate the Brunt-Väisälä frequency for mode 1 and mode 2 decreases them by 24 and 25% respectively, meaning that salinity contributes to stratification equally for both modes. These are the box plots of mode score by month again. So we've got mode 1 and mode 2, and then as a function of month. And here on the right-hand side, we have a box plot of tropical cyclone heat potential by month. I've color-coded these because I want to show you which months have not statistically different tropical cyclone heat potential. And they are June and November. So the tropical cyclone heat potential in the Gulf of Mexico in June is not statistically different from it in November. And in July, it's not statistically different from October. And in August, it's not statistically different from September. Okay? And you can see, if you squint, the tropical cyclone heat potential as a function of month is somewhat a combination of mode 1 and mode 2. It sort of follows the mode 1 trend, but not quite, because mode 1 decreases a lot further in the autumn and it starts higher in the spring. And it also has a little bit of similarity to mode 1 in this upward trajectory at the beginning half of the year. So given that regions with equal tropical cyclone heat potential have very different ocean structure, i.e. mode 1 versus mode 2 characteristic profiles, how much does each mode contribute to tropical cyclone heat potential each month? So the way that I worked this out was that I did a simple scatter plot between mode 1 score and tropical cyclone heat potential and mode 2 score and tropical cyclone heat potential. And then I just got my best fit linear regression models, which are just down here. And I used those to calculate the tropical cyclone heat potential as a function of mode 1 score and mode 2 score for each month. And so this is what I discovered. So we have the 6 months in question here, June, July, August, September, October, November, which make up hurricane season. And on the x-axis, so on the y-axis, we have mode 1 and mode 2. And then on the y-axis, we have tropical cyclone heat potential. And what this shows is that in June, the tropical cyclone heat potential is higher for mode 2 water than it is for mode 1 water. In July is also the case. Actually, maybe I should do this since I have already figured this out. So in June, July, August, and September, mode 2 has higher tropical cyclone heat, is associated with higher tropical cyclone heat potential than mode 1. And in October and November, mode 1 is associated with higher tropical cyclone heat potential than mode 2. And then if we look at this in terms of the percentage of profiles with mode 1 or mode 2 score corresponding to tropical cyclone heat potential greater than 60, we find some interesting patterns. So here we have month, all 6 months here, and then we have the total number of profiles that were recorded in that month. And then we have the percentage of mode 1 profiles that had tropical cyclone heat potential greater than 60, and the percentage of mode 2. And what you can see here is that mode 2 is has much greater representation between June and September and mode 1 has high representation in October and November. Hence, a tropical cyclone crossing a region with tropical cyclone heat potential greater than 60, which is this magic number, is more likely to be interacting with mode 2 characteristic water June to September and mode 1 characteristic water October and November. Which brings the next question. What is the relationship between mode and intensity? So in order to answer that, I used this one-dimensional mixed layer model. And so the forcing, so this was the Pricewaller-Pinkel model. It's a very simple 1D mixed layer model, which is driven through air-sea fluxes of heat, mass, and momentum. Mass and heat fluxes were set to 0, and the model was forced with zonal meridional wind stress estimated with the bulk aerodynamic formula, using the drag coefficient from Kirkik and House, and then divided those equally among the stress components. And then for the profiles, months were chosen with mean tropical cyclone heat potential. Months with the closest mean tropical cyclone heat potential were paired. So remember that June and November were not statistically different, those were paired. July and October, not statistically different, those were paired. And August and September were not statistically different, those were also paired. So that mode 1 characteristic profile, mode 1 characteristic dominant months were paired with mode 2. Okay, so we have mode 1 and mode 2 paired. Not entirely true, because actually you may recall that September was mode 2 dominant, but I paired it with August anyway. For each month, all profiles with tropical cyclone heat potential within 2 kilojoules per centimeter squared of that month's mean were identified. And of these, the 6 with the highest mode 1 or mode 2 scores were averaged to create mean characteristic profiles. And so that's what we're looking at here. So what does a characteristic profile in June look like? If you have a tropical cyclone heat potential of 39 is on the left, and then in November it's on the right. Okay, see that? And then for July and October, remember this is a mode 1 characteristic this is a mode 2 characteristic profile, and this is a mode 1 characteristic profile, and then the same here for August and September. So in each case, we have profiles that have the same tropical cyclone heat potential, but one of the profiles is from a month that's represented by mode 1, and the other one is from a month that's represented by mode 2. And then once I run the model on these artificial profiles, I can see how quickly the sea surface temperature cools. And that's exactly what you're looking at here. So I ran this for category 1 through 5. And in each figure, we have different colors representing whether it's representing the month, and if it's dashed, then it's mode 2, and if it's dashed, it's mode 1, and if it's a solid line, then it's mode 2. I know there's a lot of information here, so we're just going to zoom in on one of them. So this is the result from the PWP 1D model when I'm forcing it at category 1. And so we have, remember, June and November both have the same tropical cyclone heat potential. June is a mode 2 water and November is mode 1. July and October have the same tropical cyclone heat potential. July is mode 2, October is mode 1. And then August and September have the same tropical cyclone heat potential, but August is represented by mode 2 and September is represented by mode 1. And you should be able to see straight off the bat here that the mode impacts the speed at which the water column cools. And if we just have a close look at, for example, June and November, now remember they have the same tropical cyclone heat potential. June starts with a much higher sea surface temperature than November does, but once you force the model, this is a 26-degree line here, it only takes about 0.4 of a day, which is I guess about 10 hours for the June profile to reduce to tropical cyclone heat potential of 0, i.e. the sea surface temperature is reduced to 26 degrees. But for November, it can take days to achieve the same thing. And we could look at the same thing so this is for category 3. Not going to spend too much time digging through these images, but you can see the same sort of trend here. So if we compare, for example, June and November, again, remember these guys both had the same tropical cyclone heat potential. June starts with a much higher sea surface temperature, but when being forced by category 3 winds, sea surface temperature decreases a lot more rapidly for mode 2 water than it does for mode 1. These are the results from the model in a table form. And so this shows us the time in hours for the sea surface temperature to decrease to 26 degrees, i.e. for the tropical cyclone heat potential to decrease to 0. And just having a look at them one by one, if we compare June and November, remember these, so that June is mode 2 and November is mode 1. They both start with the same tropical cyclone heat potential, but June has an initial sea surface temperature of almost 30 degrees and November has an initial sea surface temperature of 27 degrees. If we run the model using a category 1 storm, it takes the June profile 7.5 hours to reduce the sea surface temperature to 0, but it takes the November profile 42 hours to reduce sea surface temperature. Let's say 0, sea surface temperature to 26 degrees. It takes the November profile takes 42 hours. So you can see a large difference here. For category 2, it's 4.5 and 12. For category 3, it's 2.5 and 9. We can just keep going. For July and October, the take-home message is similar. So remember, July is represented by mode 2. It's a mode 2 dominant month. October is a mode 1 dominant month. They both have the same tropical cyclone heat potential. July starts with a slightly higher, couple of degrees higher sea surface temperature. If you run the model at category 1, it takes 31 hours for the temperature to decrease to 26 degrees in July, but it would take 55 hours in October. Same sort of trend here for category 2, 3, 4, and for 5, it's no different. And then in August and September, it essentially doesn't make any difference whether you have a mode 2 or a mode 1 profile. The amount of time it takes to cool to 26 degrees it doesn't make any difference. So starting from equal tropical cyclone heat potential, mode 1 characteristic water takes longer to cool sea surface temperature to 26 degrees than mode 2. This is despite mode 2 having higher initial sea surface temperature. This dichotomy is most pronounced at lower wind speeds and when comparing early to late season conditions. And this metric here, which is the time available for vertical mixing, is 2.5 hours for small, fast-moving tropical cyclones and 22 hours for large, slow-moving cyclones. So that just gives you an idea of how long a storm is likely to be interacting with the water at any particular location in order to be able to put these in perspective. The consequence is that storms crossing the Gulf of Mexico in October and November have a greater chance of intensifying than earlier season storms. And interestingly, that this is shown in the historical record. So on the top here, we have the number of Gulf of Mexico storms from 1851 to 2019 by month. And in the bottom, it is the percentage of storms that become category 1 or above, which are in blue, and category 3 or above, which is in red. So you can see that the historical records show that most frequently we have more storms occurring in August and September than the rest of the year. But interestingly, October is the month where storms are most likely to intensify into a category 1. In fact, category 1, 59% of storms intensified to category 1 in October, and 59 versus 54 in September, August, and November. So it's interesting in that although August and September have much higher water temperatures, they're actually less likely to cause storms to intensify into category 1 than in October. And for category 3, which is given in red, you can see that August and September are the most likely to spawn category 3 storms. But when you compare October and November to June and July, you can see that October and November are much better at converting their storms into intense hurricanes than earlier in the year. Okay, so just to review, I used 415 Argo profiles collected during hurricane seasons to quantify the characteristics of the upper ocean. These data were used in a PCA, which showed that there are 3 modes of variability that explain 93% of the variance of the data. The first 2 modes were relevant to hurricanes because of their loadings for the tropical cyclone heat potential. Modes 1 and 2 describe distinct upper ocean structure with unique temporal variability. Mode 1 had higher tropical cyclone heat potential early season, and mode 2 had high, that's actually back to front. It should be mode 1 had higher tropical cyclone heat potential early season, and mode 2 had higher tropical. So that should be the other way around. Mean mode 1 and mode 2 profiles were used in a hurricane model. It was found that high mode 2 characteristic water cools more quickly than mode 1. This is especially true for weaker storms when comparing early to late season hurricanes. And storms crossing the Gulf of Mexico in October and November have a greater chance of intensifying than their earlier season counterparts. And this is shown in the historical record. And if you want more information, you're more than welcome to check out this paper, which was just published a few days ago. And if we have time, I'll be happy to take a few questions.
Yeah, thank you very much. Unfortunately, we have only 5 people left in the audience now. I don't know what's going on.
I scared everybody away.
That's really disappointing, but it was a nice presentation.
Well, it is after 3 o'clock now. We started a little late, so maybe people have other things to do.
Yeah, still there should be more people, especially more students. Brian, do you have a question? You are muted.
Well, Henry, yeah, nice work. And no, I guess I don't really have a question, Roland. I apologize for that, but
that's okay. You don't have to have a question, Brian. Well, you were kind of put on the spot.
Yeah, normally I should have had something there.
I'm impressed that your Wi-Fi or signal. Are you still at sea?
We're back in. I'm on my phone, and we're back in the port right now. The Wi-Fi is terrible.
Okay, that makes sense. I was going to say you've got really good. The Wi-Fi at sea has obviously come along great guns. You've been able to stream it. But.
Yeah.
Yeah, I see that Mathieu made a comment here or typed a question into the chat box. Mathieu, can you perhaps ask your question through the microphone. That will be better for the video if you ask it yourself than if I just read it from the chat.
No problem. Good to see you, Henry. Great talk.
Yeah, you too, Matthew. Thank you.
And so yeah, I was curious about this mode 3. I think it's striking, like it's clearly associated with the intense barrier layers, and so likely with the Mississippi River plume conditions. And
Yeah,
so,
sorry, go ahead.
Yeah. So I was just wondering if that can be used to investigate how it helps intensify storms with in case of low TCHP, which is what Jonah found in her PhD.
Yeah, you might be. So I never spent much time trying to identify mode 3, and I'm impressed that you can. Well, you say possibly associated with the Mississippi River plume, but I assume that's probably true.
I mean, yeah, you can probably check where they're located, and then you see if that makes sense or not.
Yeah, totally. So I guess in answer to your question, like there's no reason we couldn't run the PWP model on a characteristic profile of mode 3 and see how it responds. I mean, it may be that the stratification, do you suspect that it would have very strong stratification, which would reduce the mixing and sustain the surface temperatures a little bit more? Because presumably we could identify that if we just did the same sort of thing with the PWP.
Yeah, I think that'd be a great thing to try. Maybe, independently from the month, because your results were really targeted to TCHP and then to the time evolution through the hurricane season, which was great. So maybe at first, if you can run that with a typical mode 3, I don't know how much, if you will find dependency on the month, but I think
sure.
You might get something out. I think I was surprised that it was discarded. That it was discarded so early in the work.
Well, you can look at the loadings and you can see that the loading for TCHP on mode 3 is pretty close to 0. So it doesn't matter if the TCHP is whatever, 1 or 1,000. It's not really going to impact the mode 3 score, which is why I said, get rid of that. But maybe it deserves a second look or a first look, really. Thanks for the suggestion.
Yeah, thank you.
Any further comments or questions from the audience? I don't see anything, so thank you, Henry, again.
Okay, thanks everybody for coming and staying to the end.
Thanks, Henry.
And those who did not come can watch this on YouTube this evening or later. I will upload it, so I hope we will have a few more viewers there. And for those who want to know what are the next seminars, we will have 3 ATM students speaking this Friday. Then we will probably have no seminar next Wednesday because that was postponed. And then next week Friday, we have Cassie Gaston giving her candidate for tenure seminar. That will be an important one. So I hope a lot more people will be there than we have now in the audience. Of course, they don't hear me, so I can only hope. Maybe they will hear this when they watch the video.
I'm sure.
What?
Yeah, I'm sure their ears are burning.
Okay, so thank you, Brian, for watching this, and Mathieu. Thank you, Henry, for coming.
Thanks, Henry.
I hope to see you all again at the next seminar.
Okay, thanks, everybody.
I will end the recording now.
Okay. Bye, everybody. I got to go. Another meeting.